Okay, so today's class has two questions. The first question is to solve the material of this class posted on the paper already. So the first question we need to solve is an initial boundary value problem. It had a form like this. So in this problem, you can see the boundary is a non-homogeneous one. That it has a side t and two side t in each of the end here. So what we're gonna do in this question is we want to transfer the problem into another form first. There is something like this. That the boundary now become a homogeneous one. Then we solve this part by eigenfunction expansion. So how do we transform the problem into a homogeneous boundary condition? First, we let U become a combination of two functions, S and W first. That the W here, it is equal to 0 at boundary. So that means S at boundary need to equal to sine t and 2 sine t. So we let function S is equal to this. So at x equal to 0, you will get a equal to 1, and at x equal to pi. Because this pi is equal to 2 sine t, so b is equal to 1 over pi here. So the form of the function s is 1 plus x over pi times sine t. Then we substitute this s function back to the whole problem here. Yeah, I mean this part to this. Yeah. So you get this. The 0 is the second derivative of the s function, but because it only have one order x, so it becomes 0. Sorry for the mistake. So now the problem become a form like this. So what we're going to do is solve this problem by the eigenfunction expansion. But first, we treat it like this first. So again, we let the W is equal to spatial part times temporal part here. K is a positive value. So the form of x function is a combination of cosine function and sine function. And then we fit the x function into the boundary condition. So at x equal to 0, you will get b is equal to 0. And at x equal to pi, you'll get a sine k pi here. And this also need to become 0. So the k need to become a positive integer. So the function x with n is equal to an sine nx here. And then this is the eigenfunction we get. And then we use this eigenfunction to expand the non-homogeneous part with this part here. I use V to represent the homogeneous part. You can use a series of sine nx to represent the same function. And then we multiply both sides by sine mx here. And then on the right hand side, you can apply the orthogonality of the eigenfunction, that this part. is equal to pi over 2 if m is equal to n, and 0 for m not equal to n here. So now the function become this. And then what we're going to do is to solve the integral. So the integral has a form like this. First, we do the integration by part. You get the first term is equal to 2 cosine m pi plus 1. And the second term is equal to 0. Here, because the cosine m pi is equal to 1 when the m is even number, and if it's an odd number, it will equal to -1 here. And then we substitute back to the expansion. This part is the expansion for each m and the total. And the total non-homogeneous part is equal to the summation of this function. So is that okay? So what we're going to do in the next part is because we expand the homogeneous part in a series function of spatial part. Now we're going to solve the temporal part here. Again, we let because we didn't solve the temporal part before, so I use Tn to represent it. And the eigenfunction for the spatial part is psi nx here. If we substitute the initial condition, this part is equal to this is equal to 0. So Tn at time equal to 0 is 0. And its derivative at time equal to 0 is also 0. Then we substitute this W back to the form of this. So, and then we move the top SS directly to the left hand side, and we'll get T prime prime T n squared Tn is equal to, because on the non-homogeneous part we use the eigen expansion, and then we substitute the result in that part. So we build equality here. For the same n, we can solve the t for each n now. That has a modern differential equation like this. Because it is a non-homogeneous equation, so there's this part, the t here has two solutions. First is the homogeneous solution. The general solution for this equation is obvious, that is the, again, combination of sine and cosine function. And for the particular solution, because after the combination of the t and function itself and its derivative, you will get the net result has a sine t here. So we guess the particular solution also contain the sine t here. So this. And then we substitute the solution we guess into the equation. And then you get the E, which equal to this. So in the following part, we're gonna solve the coefficients C and D. In this part, we need to use the initial condition. First, we combine the homogeneous and the particular solution first. Its derivative is because in the initial condition, Ti is equal to 0. At time t is equal to 0. So the first term and the third term, because it's a sin t function, so at t equals 0, it becomes 0. So what it left is the middle term. There's the d function here, d coefficient. So d is equal to 0. And for the initial condition of its derivative, is also equal to 0. This time, because the cosine t function is at t equals to 0 is equal to 1. So what this part left is this. Because this sum here is equal to 0, so we can find the coefficient C here. So the temporal part, we get the form like this. And then we'll put this temporal part back to the function w. But what we actually want to get is the form of u. So we add back what we do in the beginning. So the result of this question is so that's how we do the question 1. Do you have any question about this? I'll give you 10 more seconds to jot it down, then I will move to the second question. Okay. So in the second question, what you're going to do is by using the linearity and uniqueness of the Laplace transform to show that the inverse Laplace transform is also a linear. So first let me write down the definition of Laplace transform and inverse Laplace transform. And its inverse is okay. First, about the uniqueness. That means if you transfer function ft into fs, and you have another function. After Laplace transform, you also get fs. That means ft is equal to gt here. And the linearity is the a and b here is any non-zero constant, and f and gt is any two function. So how are we going to prove the inverse Laplace transform is also linear? First, let's say we have a function ht here. There's the combination of two functions, ft and gt. Again, a and b is some non-zero constant. And ft, gt again is any two function. If we Laplace transform the ht, it's actually the Laplace transform of the right hand side too, because ht is equal to the combination of this. And then we apply the linearity of the Laplace transform. So you get a function f and g in S space. That means the ft here is. And then if you inverse Laplace transform the result, because of the uniqueness of the Laplace transform, after you transform this into this, if you transform this back to using the inverse Laplace transform, by the definition, you should get back this form. But AFT plus B times GT is actually is the inverse Laplace transform of the Fs and GS function. So you get a relationship that the inverse Laplace transform is also a linear operation here. So that's how we prove that inverse Laplace transform is also linear. Do you have any problem about second question? It seems no one have any questions. So if you have any question, you can stay here and ask. If not, you can go now.